4.2 Polynomial Functions. In this section, we are going to learn how to recognize the polynomial functions and understand the characteristic of the graph of the function. Find the zeros of the polynomial function by factoring. Determine the end behavior, and by the end, we graph the polynomial function without using the calculator. So how can we tell the function is a polynomial function or not? So we look at the definition of the polynomial function. A polynomial function in one variable, right? It has an x, is a function of the form your function f of x has a sub n multiply x sub x with the power n, an minus 1, and a1, a0. They are all coefficient number. And the an we give a name is a leading coefficient. Leading coefficient. Because this is a number of the highest degree power term. So n is the highest degree of the function. The polynomial function has that descending order pattern of the entire function. For example, the function, the highest degree power of the function, let's say is power 4. And then the following term is x power 3, x power 2, x, and then it's a constant term. Sometimes you might have one term is missing. That is okay. We can have the 3x power 4 plus x squared and then plus 1. This is a polynomial function as well. So as long as they have that descending order pattern. Another thing is the polynomial function, the degree power must be a whole number. A positive integer, in other words. So n is a whole number. There's no negative number, there's no fraction form, there's no radical form. No, only the integer, the whole number, can display on the degree power term here. So throughout the entire function, the degree power term must be an integer. Now we look at the example. The table here shows the examples of the polynomial function. So we can, on the left hand side, all the functions here, they are polynomial. The other side, they are not. So we look at the first one. F of x equals 5. 5 is a constant number, right? But in fact, f of x equals 5, I can rewrite a 5 to multiply with x power 0. X power 0 is equal 1. So with 5 multiply x power 0, 0 is a whole number, right? So this is a polynomial. And that's why you don't see the x term here, but in fact, just a number, a constant number still carry, we still can count that a constant number as a polynomial function. It's because it's degree 0. The function has 3 over 5x minus 7. Since this x term has a degree power is 1, so this is a polynomial. Negative 2x squared, this is a positive integer, right? Plus 4x, x has a power 1, this is a positive integer. Minus 5, 5 has x power 0, so this is a positive integer. So all the 3 degree power, they are positive integer, so they are polynomial function. The next one, 1 over 2 x power 3, this is a positive integer. The next term has power 2, this is a power 1, and this is a power 0. So yes, this is a polynomial. So they are polynomial. This one has -5 multiplied with x power 4 integer, right? Positive integer. Now the following term, the coefficient number is square root 2. That is okay. For coefficient number, we can, it could be a fraction form, it could be a decimal, it could be a radical number. As long as they are the real number, that is okay. The only thing we consider is the degree power term. So as long as I make sure all the degree power number has a positive integer, then that is a polynomial. All right. Now we look at the other side example here. The g of x function has a root x minus 2. Now, when you have the square root sign of x, when I convert, or the other way to represent the square root x is x to the degree power half. Now, half is not an integer, right? It's a fraction. And that's the reason why this is not a polynomial. Same way here. This one has a cubic root of the x. So the cubic root of x, when it's the same presentation, you have the x to the degree power 1/3. So 1/3 is not an integer, it's a fraction. So g of x, this is not a function, not a polynomial function. Another example here, 2 multiply x plus 4 with the absolute value. Now, with the absolute value here, this is a particular form, right? Your x is inside of the absolute value. So this one, we don't count this one is a polynomial function because the graph of the absolute value is a V shape and it comes with a sharp corner. It's a V shape. This point is not a smooth curve, right? Polynomial function must be a smooth curve. But absolute value has a V shape. There's a sharp point here on the vertex. So we don't count absolute value is a polynomial function. G of x is 2x over x squared minus 4. This is a rational function. And when we have the rational function, there's an asymptote. There's an asymptote in the between. So this one is not a polynomial. This function has 3 times x to the power -2. So we stop here because this -2 is not a positive integer. So we don't count this one as a polynomial. The last one has the degree power is 2 over 3. So this is not a polynomial. So we stop. So the way you recognize the polynomial function or not, just simply by looking at the degree power term. When the degree power is a positive integer, then we count that as a polynomial. So we do a practice here. Example A, f of x function. How can we determine this is a polynomial or not? X, the highest degree power term is 6. This is an integer, right? This is an integer. 5 times x, this is an integer. Root 2, there is no x term, but we count this as x0. So they all have the positive integer, which means the whole number. So example A is a polynomial. Look at the g function here. The highest degree power term is number 8, right? Degree power 8. So this is an integer, positive. The following term has x power 4. This is a positive integer. However, the last term here, it has 3 over x. Now, 1 over x, the way you perform, or the other way to represent it, is x to the power -1. So when you have 1 over x squared, this is the same way you represent it. You have the x to the power -2. So when I have the 10 over x, this is the same meaning. I have the 10 to multiply 1 over x. Now 1 over x is a power -1. So just because of this term is a 10 to multiply x to the degree power -1. So this function is not a polynomial. Even though the other two they work, right? They are polynomial, but this term is not. As long as there's one term is not a polynomial pattern, then we have to exclude or reject the function is a polynomial. Look at the C. The first term has power -4, so we stop. This is not a polynomial. Alright, now we move on to the next one. Understand the characteristics of the graph of the polynomial. So the first characteristic, the graph of the polynomial function is a smooth and a continuous curve. So as here you can see, throughout the entire curve, it's a smooth curve. There's no gap, there's no open circle, right? Or there's no cut. So they are all smooth curve. And that is the characteristic of the polynomial function. The second characteristic, okay, this slide just gives us the idea what kind of the graph is not a polynomial. If you look at this curve here, we call this as a cusp. The cusp, that means it has one part of the graph is a curve, and then it comes with a sharp corner. So in that case, we call this is a cusp. A cusp is not a polynomial. If you look at this graph, here has a gap, right? So there's a discontinuity here. So this is not a polynomial. Plus, there's a hole inside of the curve. So this is not a polynomial. The second characteristic, the polynomial graph has a specific end behavior and will either rise or fall on the far left and the far right. So it has an end behavior of the polynomial function. So if we will look at this function here, the end behavior toward to the right hand side forever, the other side is toward to the left hand side forever. So we will give the name is as x increased to as x approach to infinity, right? The x, it will keep going to the right hand side forever. As x approaches to positive infinity, f of x will approach to positive infinity as well. The other side here, as x approaches to negative infinity, because it is a negative infinity, here is a positive infinity, f of x approaches to negative infinity. It will keep going down forever. So we call that is the end behavior. This one, if we look at the end behavior of this graph, both of the end behavior, they go to the positive infinity, right? This is a positive. So the way we interpreted the end behavior of this graph, we write down as x approaches to positive infinity, right? This is positive infinity. F of x approaches to positive infinity. As x approaches to negative infinity, f of x approaches to positive infinity. So this is the end behavior of this graph.